Okay, guys, moving on a little bit. We talked about the mole, and we talked about how the mole could be related to mass, where we find one mole is this 6.02 times 10 to the 23rd particles, right, in one mole. And if you want to count those particles out, you simply go to the periodic table, you grab the masses from each element, and then you have with 1 mole. So as long as you take those masses off the periodic table, you would have 1 mole of particles. Okay. And you can do that for various substances. And we talked about the fact that if you had a liquid or even a solid and you wanted to find how many particles there were, you could simply use a scale and weigh them, right? So that would be mass. However, if we want to use gases, sometimes it's helpful to equate a mole to the volume or the space that a gas takes up. Again, gases are a little tough to weigh, a little tough to manage when it comes to weighing them. So if we can equate their volume to this, that would be kind of useful. So we look at something called molar volume, and this is going to be for gases only. All right, so we know that gases are going to expand to fill a container. And when you fill a container, we're talking about the volume of a gas, right, in their container. All right, that's important to know. So if we can define a certain temperature and pressure, okay, of this, all right, and we know that a certain temperature and pressure gases will be set at a certain volume, and we can define that temperature and pressure, say STP. I'll go to that in a minute. We're going to find out that 1 mole of any gas. Okay, so any gas, and again, as we look a little further into gases, we'll see this. But a mole of any gas, okay, will always take up about 22.4 liters. Again, with some significant figures here, at STP. So again, 1 mole of any gas will be up 22.4 liters. Now again, that 22.4 liters in that 1 mole is still 6.02 times 10 to the 23rd particles. So again, you're still counting them. It's just you're counting them by volume instead of counting them by mass. Okay, again, we talked about those apples. Those apples could be counted by mass, right? We could weigh them. And we can also put those apples in a basket and find out how much those apples would fit in the basket. All right, so STP is called standard temperature and pressure. Okay, and this is only true, this 22.4 liters will be true when the gas is at 0 Celsius, so 273 Kelvin. Okay, and when these pressure units are satisfied. Okay, and this is pressure. This is gas pressure. This is the force that gases place on their surroundings. Okay, so 1 atm, 101.3 kilopascals, 760 millimeters of mercury, 760 torr. These are different units of pressure. So as long as one of these is true and one of these is true at the same time, gases will take up 22.4 liters. So we're going to assume that this is true. Okay. If you do change the temperature and pressure, again, you will change this volume. Okay. So really important to know this. All right. So just a little visual on this. Let's just say I had 22.4 liter. I had 1 atm. I had 273, 1 atm, 273, 1 atm, 273 for 3 different gases. Okay. And if I had 22.4 liters of them in these boxes, okay, this would take up 1 mole. So you'd have 1 mole of particles in this box. Okay, 1 mole, 1 mole. Okay, and again, this would be 6.02 times 10 to the 23rd particles. This would be 6.02 times 10 to the 23rd particles, and this would be 6.02 times 10 to the 23rd particles. Okay, as long as you can get so actually, it's kind of interesting that we can count again by volume, as long as this is true. Okay, now it's important. Good. All right. Couple of things you want to realize is that now really, what's weird here is what's different is the mass. So notice that the temperature, the pressure, and the volumes are all the same. Then you have the same number of particles, but the mass is going to be different. If you add these together and you get the GFM of carbon dioxide would be 44. If you add them together, you get 44 grams per mole. This would be 2 grams per mole. Don't forget the 2 here. Okay. And xenon is 131. So xenon is 131 grams per mole. All right. So notice that everything is the same here except the masses. That's the important thing. And Amadeo Avogadro was involved in coming up with the theory of these gases having the same number of particles. So he came up with a hypothesis, and his hypothesis is simply equal volumes. Okay, and again, this is going to be important to get this kind of this vocabulary straight. It looks more wordy than it actually is, but equal volumes. Okay, so all your volumes are the same of gases at the same temperature and pressure have the same number of particles, and the key is same number of particles. So basically, as long as you can compare different gases. If you have the same temperature and pressure, then you can be sure you have the same number of particles. Okay, and again, if you had 1 mole, this would be locked in at 22.4 liters. Okay, the only thing they're going to have is their masses will be different depending on the GFM. Again, the GFM, okay, are different, right? Because they have different molecules, different elements in them, and different elements have different weights. We know that already. All right. So a good way to see this, a good way to question this is looking at this little regions question here. Again, the data table below shows the temperature and pressure of 4 different gas samples, each in a 2-liter container. Okay, and the key is you're in a 2-liter container. Okay, so because we're in a 2-liter container, we know all the volumes are the same. Okay, so again, this is 2 liters, this is 2 liters, this is 2 liters, and this is 2 liters. All right, so we know that the only way, it says which 2 gas samples contain the same total number of particles. Well, if we know the volume is the same for all of them, well, Avogadro's hypothesis say that if you're going to have the same number of particles, you must also have the same temperature and the same pressure. So the only elements that have the same temperature and pressure here are, if we look carefully, we'll see neon right there and methane, those 2. So those 2 have the same volume, same temperature, and same pressure, so they must have the same number of particles. Now, again, we don't know how many particles because it's 2 liters, but we know they're the same. All right, so that would be, let's see, neon and CH4. Neon, CH4 would be choice 2. Okay, so that's a good example of this. So again, what's the point? The point is 1 mole of any gas at STP is 22.4 liters, okay? And of course, if it says 1 mole, it also must be 6.02 times 10 to the 23rd, okay? You don't have these particular questions on your packet, but I figured I'd just look at them, again, in a different way. I believe this is the same question we did before, but if you look at these 2 different ones, again, these are just classic examples of these types of questions. Which gas samples at STP contain the total number of molecules in 2 liters of CO2? Okay, again, we want to make sure that, again, same total number of molecules in 2 liters. If they're all at STP and you want the same number of particles, you have to have the same number of volumes. So with 2 liters, the volume must match that volume, so it's choice 2 again. Okay, which 2 samples at STP contain the same number of total molecules? The volume must be same. Okay, so again, volumes are different. Volumes are different. Volumes are different. Here's where the 2 liters matches the 2 liters, and you have the same of everything. Okay, so again, you're looking at those same things, and again, this was the same thing we had neon here. If you're also in 2 liters, we had the same number, same pressure, same volume, choice 2. Okay, so I know this is a quick slide here, just a quick. So we've pretty much looked at everything as far as is defining the mole. The mole, again, can be defined as 6.02 times 10 to the 23rd particles. We can also use the mole for mass and say that it's the GFM, right? The grams per mole off the table. And we could also say that we also have 22.4 liters is a mole, okay, of any gas. So we've covered all the bases. Time to see what the mole can do, and that's going to be in the next lessons.